And welcome to today's lesson. In this first tutorial, we will be able to attack all four of these objectives. We will find the equations of vertical and horizontal asymptotes. We will graph our rational functions and be able to check them in the calculator. We will state the domain and range for our rational functions, and we will state the end behavior for our rational functions. So we are in sections 8.2 and 8.3 in our textbook, at least the first half. We're going to spend 2 days on this topic. Let's first start off with some vocabulary. We're talking about rational functions still in this chapter, and a rational function is a function that can be described basically as a fraction. We have p of x divided by q of x, and since we have a denominator, that is very important to understand that the denominators can never be equal to 0. This will help us when we're talking about our domain. Okay, any values that happen to make the denominator 0 have to be taken away from our domain, and they become our vertical asymptotes. The value of a rational function is undefined for any domain point, I'll just call it A, that makes the denominator equal to 0. That's the big no-no. These equations, x equals a, that's the equation of a vertical line, is called, or they are called, vertical asymptotes. So that's how we find our vertical asymptotes. An asymptote, I like to think of an asymptote as simply a boundary line. It's a line that the graph is going to be infinitely getting closer to, infinitely approaching, but it will not touch. Okay, now I put almost always. Vertical asymptotes will never be touched because the function is not even defined there. But I put almost always because some horizontal asymptotes will be touched, and we'll look at one of those examples in a later tutorial. The domain and the range is basically what we've talked about before. The domain is the set of all of the x values, or our inputs, that satisfy the equation, and the range is the set of all y values, or our outputs, that satisfy the equation. When we first start talking about our rational functions, we're going to put them all in HK form. So let me give you what HK form is. Let's say we have our function f of x. HK form would have a divided by x minus h, and then we're going to add k to it. When it's in HK form, it's really simple to find the equations of our two asymptotes. So let's talk about the vertical asymptote first. Make sure you're spelling asymptote correctly. There's a P in that word. Vertical asymptote. Okay, the vertical asymptote is always going to be the denominator, is always going to be the value that makes the denominator equal to 0. So in this case, that would be the value of h. It's very similar to all of our other parent functions where we're taking a value out of the symbol, as it were. Here, if you had parentheses, it's always the opposite of that symbol, the minus sign, so that means that h will be positive. Our vertical asymptote, I'm going to label it as VA, vertical asymptote, is the equation x equals h. Remember to always make it an equation, and in this case it's the equation of a vertical line. A horizontal asymptote, that's going to be the value of k. And I'm going to label that with HA. And no, that's not because I made a joke. Okay, HA for horizontal asymptote, not ha. It's going to be the equation of a horizontal line, which is y equals, and it's just whatever the value of k is. If you see a positive 3, it's 3. If you see a negative 3, it's negative 3. So it's just y equals whatever k is. So when it's in HK form, it's pretty easy to find the equations of our horizontal asymptotes, and let's show you how in this first example. So we have our f of x, our rational function. It's in perfect HK form. Let's first start by finding our vertical asymptote and our horizontal asymptote. The vertical one comes from the denominator, and in this case it would be negative 3 plus 3 that would equal 0. So that's why x equals negative 3 is the equation of our vertical asymptote. What I'm going to do is go to the x-axis in my graph to where x equals negative 3, and I'm going to dash in a vertical asymptote. I prefer that you dash these in. It's technically not part of the graph, it's just a boundary line for the graph to approach. Next, let's find our horizontal asymptote. I'm going to try and color code. If you have a couple different colors, that would be great for your notes. The horizontal asymptote is always going to be k, and k is a -1, so y equals -1. Similarly, I'm going to come to the y-axis to where y equals -1, and I'm going to dash in this horizontal line. Now we're ready to put the parts of our curve into our graph. When we're in standard form, the last thing that we can use to help us with some of the points on our graph is the numerator, is the value of a. And in this case, a is 2. And what I like to do with that is I like to find the kind of the intersection of my two asymptotes. And whatever a is, I'm going to count 2 to the right, and then we get to go 1, in this case up, or I'm going to go, I'm going to go 2 up, and then I can get to the 1. Because there is a part of the curve that comes right in here, and I'd like for you to get a couple points, if you can, of that curve. Now notice that I'm curving this infinitely closer to this vertical asymptote, but I'm not going to touch it. I'm okay with your little arrowhead touching it, of course, but the actual curve is not going to touch it. I curve a nice smooth curve through these 2 points, and I'm also getting closer and closer to this horizontal asymptote, but I'm not going to touch it. I'm not going to get sloppy and do something like this where I curve and then start to curve away from that. That's no good. Please don't do anything like that. I will have to take off for that. An asymptote is something that the curve will infinitely get closer to, so you're approaching it infinitely. Okay, so the same sort of thing. I'm going to go to the intersection here, and I'm going to count out 2 units so that I can do 1, and then I'm going to count down 2 units so that I can do 1. And it's basically going to be a nice symmetrical part of the curve. I'll just do a little part of it right here. And that's our first rational function. Let's talk about domain and range. I'm going to color code. My domain is everything except for -3. That's the only value in the domain that x cannot be. Every other value is fine. I like to do set notation, so I'm going to start off by saying the set of all x such that x is not equal to -3. That's a perfect way to describe the domain. Some people like to do interval notation, and in this case you'd be describing 2 intervals, everything from -infinity up to -3, and then everything from -3 to +infinity. So we start with -infinity, and we go to -3. Now we have to use a parenthesis because we don't get to include -3, and then we use our union, and then we pick back up with -3 with the parenthesis and go the rest of the way to +infinity. Either one of these is acceptable for the domain, set notation and interval notation. I'd like for you to be familiar with both, but you don't need to write both every single time. Pick whatever one you like. Again, I like to do domain and set notation because it's just a single little restriction. Let's talk about the range. Very similar with the range, there's only one y value that our graph cannot be equal to, and that is this value of -1. So similarly, I'm going to use set notation. This time it's all y, such that y is not equal to -1. If I wanted to, I could describe 2 intervals up the y-axis from -infinity to -1, and then from -1 to +infinity. So I could do that as well. Remember, use parentheses in your union. Parentheses means that you're not including that value of -1. And our last thing is end behavior. Our end behavior is what is happening to our graph at the very far ends. Remember, there's 2 ends. We go all the way up as x approaches +infinity, and then we go all the way to the left as x approaches -infinity. So on the far right end and on the far left end. Okay, so I know that end behavior starts off with as x approaches. In this case, I know that both ends do the same thing, so I'm going to do plus or minus. Okay, both ends, the right end and the left end. And if you notice, look what's happening. This time, our graph is not approaching infinity or approaching -infinity. It's actually trying to level out. It's trying to touch this horizontal asymptote. It's never actually going to touch this one, but it's trying to be that value, and that value is -1. So the end behavior at the very far end, at the right end, we're trying to be equal to -1. And at the very far left end, you can see that the graph is coming up. It's trying to reach this horizontal asymptote. It's never actually going to touch this one, but it's trying to be -1. So it doesn't matter which side we're on. As x approaches plus or minus infinity, the function, which in this case is f of x, is trying to approach -1. And that's our end behavior. So there's our first example. Let's try this again with example number 2. Here's example number 2, g of x. Let's first start out by finding our vertical and horizontal asymptotes. Our vertical asymptote, I want to make sure I'm doing the same color. Nope, our vertical asymptotes were red, so let's undo that and go to red. Vertical asymptote, in this case, the equation is going to be x equals -1. So I'm going to go to my graph to when x is -1 and dash in a nice vertical line. Change my color for my horizontal asymptote. In this case, my horizontal asymptote, the k is 3, so y equals 3 will be my horizontal asymptote. 1, 2, 3, and I dash in my horizontal asymptote there. This time, if I'm going to use my little value of a here, a is a -1, and since it's negative, we're actually going to be flipping the graph. It normally would be a curve in this section and in this section, but in this case, because a is negative, it's going to flip and it's going to be in this section and this section. It's only going to be one, I get to the intersection of my asymptotes, it's only going to be one away before I can get up to the 1, or one away up and I still get to the same point. And the same thing here, down 1 and over 1, or right 1 and down 1. Those are going to be my two sections, just one point in this case.
You can't touch this.
Something's happening here. Try this again.
You can't touch this.
Just make a nice smooth curve. Again, approach your asymptotes, but don't touch them and don't curve away from them. There we go. I'm okay with the arrowhead touching it, that's fine. Now, I have experience graphing these things, so I knew that. We're going to use our calculator to check ourselves. So I'd like to make sure that this is actually correct in our calculator. The only thing I want to make sure of, let's actually go back to example number 2 and check in the calculator. When you're plugging things into the calculator, you need to make sure that you have anything that's in the numerator in parentheses and anything that's in the denominator must be in parentheses. Please make sure that you're using your parentheses. So if I'm going to check example number 1, the numerator is just a single thing, so I don't need parentheses around that, but the denominator is an x plus 3, a binomial. The calculator needs to know that, so you need to tell it by using parentheses. So let's pull up the calculator. Let me slide it over here. Whoa. Let me slide it over here, and let's plug this into the calculator. Turn it on and make it a little bit bigger. Let's go to y equals, and let's plug this in. I've got 2, and then when I push the divided, I need to plug in my parentheses and put the x plus 3 in parentheses here so that the calculator knows that it's the denominator, and then I can do my minus 1. We can all press zoom 6, at least this first time, so that we can have our standard screen and we're all looking at the same thing. Mine happens to be blue. And there's the graph. Now, is that what our graph looked like before? There we go. It's not going to graph the vertical asymptote or the horizontal asymptote, but the rest of the curve should look like what we've already graphed. And there we go. Let's check the second one. Plug this in. Let's go back to y equals. I'm going to clear out that first one and plug this one in. We've got -1. When I hit the divided, I need to remember to put in parentheses x plus 1 and close that set of parentheses before I do my x plus 3. And then I can press graph. And let's see if that's what I get. Yep, there it is. Again, it's not going to graph the asymptotes, but it's a good way of checking yourself. I would use it at the end to check that you've done everything correctly by hand. Okay, let's do our domain and range and end behavior. Our domain here, I'm going to do in set notation, all x such that x is not equal to -1. And let's do our range, which is very similar except that we're talking about a different variable, y, all y, such that y is not equal to, I can see it from here, 3, or I can count it on my axis, which is 3. If you want to do your set notations, that's great. If you'd rather do interval notation, I'll go ahead and put those in here just in case, if you like to be an interval notation person. Or we could do interval notation with this. If you're going to choose interval notation, I feel like it's a little bit more writing. Please don't forget your symbols. And finally, end behavior. Again, both ends, well, basically all the rational functions, both ends are going to be doing the same thing. So I can always start off rational function end behavior with as x approaches plus or minus infinity, because both ends are going to do the same thing. Let's see what both ends do this time. On the very far end, this end, the right end, we're trying to approach the horizontal asymptote, which is the value of 3. And in the very far left end, same thing. We're trying to get to 3. In this case, it's g of x. So g of x is trying to approach to 3. And it's not ever actually going to be there, but it's trying to get there. That's our end behavior. Thanks for watching this, and we're going to look at a couple more examples in our next tutorial.